Good afternoon and welcome to today's webcast titled Case Studies on Implementing Low-Cost Modifications to Improve Nutrient Reduction at Wastewater Treatment Plants. This webcast is sponsored by EPA's Watershed Academy and EPA's Office of Wetlands, Oceans, and Watersheds, also known as OWAW. I am Ann Weinberg with EPA's Watershed Academy, and I will be co-moderating today's webcast along with Tim Connor. Tim is a chemical engineer in the EPA's Office of Wastewater Management, and I want to also thank all of you for joining us today. First, we're going to start by going over a few housekeeping items. First, I'd like to briefly summarize some of the features of today's webinar. We hope you will all ask a lot of questions. Please type your question in the questions box on your control panel and click Send. If the control panel is not showing, simply click on the small orange box with the white arrow to expand it. If you have any problems viewing the broadcast or can't hear it, just let us know in the questions box and we will post an answer in that same box. This webcast will be archived for later viewing on EPA's Watershed Academy webcast page at www.epa.gov Watershed Academy. You might notice it looks a little different. It is now in Drupal. A PDF copy of the slides is also posted on the Watershed Academy website. And participants are eligible to receive a certificate for their attendance at the end of the webcast. Directions for obtaining this certificate will be presented at the conclusion of the presentations. And I want to note that the materials in this webcast have been reviewed by U.S. EPA staff for technical accuracy. However, the views of the speakers and the speakers' organizations are their own and do not necessarily reflect those of U.S. EPA. Mention of commercial enterprises, products, or publications does not mean that U.S. EPA endorses them. Now we have completed the discussion of housekeeping items. Let's kick off today's webcast. As many studies have shown, nutrient pollution is one of America's costliest and most challenging water quality problems. However, many of the nation's wastewater treatment plants were not designed for nutrient removal, and major retrofits may be a significant hurdle. During this webcast, we will highlight EPA's recently released draft report, which showcases a number of communities that were able to achieve better nutrient treatment of wastewater treatment plants through relatively low-cost modifications without requiring costly infrastructure upgrades. The webcast will give listeners a broad overview of the report and will highlight two of the case studies in Crewe, Virginia, and Victorville, California. We have a highly esteemed panel of speakers with us today. For the full bios, please see the webcast flyer on the Watershed Academy website. So without further delay, let me briefly introduce our speakers. Our first speaker is Dr. Ellen Galinsky. She is a Senior Policy Advisor at the U.S. Environmental Protection Agency's Office of Water in Washington, D.C. She will introduce our webcast. Victor D'Amato is a Senior Engineer at Tetra Tech, Inc., and he is located in Research Triangle Park in North Carolina, and he will provide an overview of this draft report. And we have also John Rico, who is a superintendent of water utilities in the town of Crewe, Virginia, and he will share highlights of his case study. And finally, we will hear from Gilbert Perez, who is the Director of Operations at the Victor Valley Wastewater Reclamation Authority in California. I want to thank all of our speakers for joining us today. And one final note, before we kick off the presentations, we'll try to answer as many questions as we can, but we have a large number of attendees, we may not get to all the questions. But the speaker's contact information is on one of our final slides, and please do contact them if your question did not get asked. And with that, we'll begin our presentation. I will now turn it over to Dr. Galinsky to provide an introduction to our webcast. The floor is yours. Take it away.
Thanks so much, Ann, and I really appreciate the opportunity to be here today to set the stage about the study and why we did it, and then I'll turn it over to the experts to talk about the technical aspects and some of the results of the report that I know many of you are interested in. So as Ann said, nutrient pollution is a very serious and costly and widespread problem in the United States as well as really throughout the world. Impacts to water bodies from nutrient pollution are well documented. They affect environmental and economic viability of our waters and affect tourism, real estate values, and commercial enterprises. Also the quality of our waters for fishing, swimming, and recreation, and also public health, including nitrates in drinking water and algal toxins in drinking water. I know you've all heard about a lot of those instances on the news. So the challenge before us is how we can most effectively work and collaborate at all levels to address sources of nutrient pollution. And EPA is working very closely with the states to develop nutrient reduction plans for each state that look at, prioritize their sources of nutrients and also where those nutrients are going and how they can be controlled, and sort of work in a sequential way. So this webinar is going to focus on the point source opportunities from treatment plants to reduce nitrogen and phosphorus going into our waters. So cost is, while the technologies are there for nutrient removal, cost is often seen as a barrier to enhancing nutrient removal at community wastewater treatment plants. Excuse me. So that the high cost is typically associated with building new infrastructure and retrofitting facilities and operation and maintenance costs to achieve significant nutrient reductions. Of course, if you're building a plant from scratch, it's a little bit easier to incorporate those advanced nutrient removal technologies, but they're still expensive. And in some cases, getting down to the small level of nutrient concentrations that's required to meet water quality standards in a particular water body requires very costly investments. For example, if the treatment plant is the primary source of nutrient loads to a water body impaired by nutrients, you're going to have to get down to really low levels, and that can be either very costly to have equipment, or sometimes the equipment just won't get down that far. So we really believe that there are circumstances where you can make incremental improvement to nutrient removals in order to make progress on delisting impaired waters, and you have some flexibility if your state gives a variance based on cost, economic impact in meeting water quality goals, and gives you more time to meet those goals. So those are circumstances where optimization becomes appropriate, because it can be considered when permit authorities are seeking to make progress on reducing nutrient discharges, but don't have to go from all the way at one time. So why did we think about this report? We were talking amongst ourselves here at EPA, our EPA regions, and many of the state water directors started talking to us about, is there something we can do to optimize wastewater plant performance without doing changes to the infrastructure that could be costly, or maybe they're 10 years down the road for that particular municipality. So we were asked if there were any case studies out there that could be used in a dialogue with communities to show them that what opportunities there are for POTWs to make low-cost modifications and to incrementally reduce nutrient discharges. So EPA developed this draft study to help fill existing gaps in information about these low-cost techniques. We're really grateful for the number of communities that willingly shared their successes for these case studies. I'm guessing they're pretty proud of what they were able to do with their existing equipment and to avoid capital costs. So I think we were pleasantly surprised with the number of case studies we were able to come up with, and we're still looking for more, by the way, if anybody has them. So what we found in the report, and the other speakers will be going into this in much more detail than I am, that optimization for nutrient reduction is feasible and cost-effective under certain circumstances. and that low-cost activities can be implemented at existing wastewater treatment plants. We're finding more examples for nitrogen than for phosphorus. So again, if you have examples for phosphorus, please let us know. And in many cases, we're getting a twofer, actually a threefer, because in addition to reducing nutrients, energy efficiency is increased. We're using less energy and also reducing operational costs and improving process stability. So it's a win-win-win-win here. So low-cost nutrient reduction improvements, particularly for relatively basic treatment systems, are underreported in the literature. We found that. So again, if you have basic treatment systems that you're able to tweak for nutrient reduction, we'd love to hear about that as well. So next steps, we released the draft report in August 2015, and the web address is on your presentation. We did it as a draft because we're seeking more data for an updated version. And we'd like to collaborate with others who are interested in POTW optimization, if you are. So we've already received several new case studies, shows you where to submit case studies or comments, or you can always give us a call. I guess we'll have some phone number to do that at the end. And we also want to explore how to better align this work with efforts to improve energy efficiency at treatment plants. For example, our Region 4 out of Atlanta, the southeastern states, are working with states and communities to reduce POTW energy consumption and optimize nitrogen removals. So with that, I can take a pause if there's any general questions, but I know you're also anxious to get into the technical presentations.
Okay, thank you, Dr. Galinsky, for providing that excellent introduction to this webcast. We're now going to have not a lot of questions coming in yet, so we do encourage you to send in questions now and throughout the webinar. Is there anything, Tim, any questions you want to pose?
No, I'd like to thank Dr. Galinsky. Thank you, Ellen. That was fantastic. Really appreciate you coming in.
Thanks, and I hope you all learn a lot from this webinar. Thanks for taking the time to sign in.
And I only will say that folks that are putting in questions about the technical aspects of it will continue to respond to you as we can. And thank you all for your persistence if you've had some troubles, but it looks like we're doing pretty well. So I think we should proceed.
Okay, again, thank you, Dr. Galinsky. And now we're going to move along here to our second speaker. We're going to have Victor D'Amato, who's going to provide some more background on this recently released EPA draft report. So, Vic, take it away. We're going to be seeing Vic's slides in a few. Vic, take it away. The floor is yours.
Greetings, everyone. Sorry for the technical difficulties. Glad to be here, and thanks to Dr. Galinsky for the great introduction to the project. I'll hit on some of the points that she made, especially at the end, but I've got about 20 minutes to provide basically a more detailed overview of the report, the methods that we use to identify case studies, as well as summarizing the findings. And then, as you know, after me, we'll hear directly about two of the case studies direct from the source. So we'll get started. So as you heard, the focus of this study and report was on low-cost modifications that are being and can be done at wastewater treatment plants to improve nutrient removal and reduce nutrient discharges, and really specifically looking particularly at wastewater treatment plants using relatively basic technologies. In other words, plants that were not already designed for enhanced nutrient removal or specifically designed for that. So although there's a lot of information in the literature, engineering texts, and so forth, kind of providing the background, as far as we can tell, this represents one of the first or only documented efforts to really present empirical, that is real-world data focused on these types of facilities and these types of low-cost optimization efforts. So although there is a substantial amount of background information presented in the report, the focus is really, again, on the case study facilities, what they did, how it turned out, and especially how their experiences can inform your efforts, you being perhaps regulators or managers and operators of wastewater treatment plants in particular. So I'm going to start by documenting the case study identification and selection process. I'm not going to read through this list of activities here, but suffice it to say, we believe we did a pretty thorough search for potential case studies without actually getting out and going from plant to plant and so forth. As part of our case study identification and selection process, we evaluated potential case studies for various criteria. One was the responsiveness to the project objectives, or the responsiveness of that particular example or case study to the objectives. And again, kind of harping on this, but that included starting with relatively basic or non-advanced, particularly from a nutrient removal perspective, treatment plants, and then improvements in nitrogen and or phosphorus reduction using relatively low-cost techniques, mostly optimizing what they already have. The other piece there is the availability of appropriate data. So anecdotal information is great, but we really wanted to have some real numbers. And in this case, what we were targeting were influent and effluent monitoring data for TN and or TP, preferably for a couple years, 2 to 3 years before and after optimization. The other important piece of data that we wanted to have was good documentation of costs and or cost savings associated with these types of efforts. And then finally, we were mindful of trying to represent a diversity of scenarios. And by that I mean different geographies, certainly different plant types, and you'll see that we put some effort into trying to collect information for different plant types, not always successfully, as well as different optimization approaches that we'll get into shortly. So what did we find? Our master list of potential case studies included over 80 wastewater treatment plants. However, we ended up eventually using 12 total case studies in the final report. Of those 12 case studies, we would say that 7 fully met the criteria that I presented on the previous slide. However, the remaining 5, the project team felt were still worthwhile to include because they helped illustrate and communicate sort of a broader range of scenarios and nutrient optimization approaches, even though they might have fallen short on being perhaps a more advanced treatment process than we were targeting, or maybe a more expensive and intensive type of effort to improve nutrient reduction. So the process of going through and trying to identify and evaluate potential case studies revealed some very important things. I appreciate what Dr. Galinsky said about being excited to wind up with 12 case studies. However, I think from my perspective, we found less than we thought, especially with the plants that were not activated sludge plants. So, we feel like that kind of illustrates one of two things. One is, that, at least in my mind, that these types of efforts to optimize our less advanced wastewater plants are less common than we thought. And I don't necessarily think that's the case. I think the next point is more likely is that a lot of these efforts, again, particularly at the less advanced treatment plants, which may be smaller plants, are uniquely underreported and underdocumented. And I think that ended up being pretty clear, especially just based on the first step of the process, which was a literature review. Certainly found that the vast majority of the efforts documented via literature search really focused on either higher tech or more costly nutrient removal improvements or optimization of plants that were already designed for nutrient reduction. And this does make some sense. These types of facilities that are documented and they have more resources, hire consultants more routinely, and are just more likely to publish their results. It's not a bad thing at all, but it does imply that there's a great opportunity for us to dig deeper, like we're trying to do with this effort, to identify things that treatment plants with less resources are doing to improve performance, particularly in the nitrogen or nutrient removal arena. So with that introduction to the case study selection process, we'll switch gears a bit and get into some of the details of our findings. But before we do that, a very, very quick and basic primer on wastewater treatment, mainly to introduce the 3 major classifications of systems for which we attempted to find applicable case studies. So activated sludge, very common, is depicted in the top left photo. It's something we call it the suspended growth process. What that means is that the contents of that tank, the aeration tank, something we call mixed liquor, is basically a combination of the influent wastewater coming in, microorganisms that treat the water, and those are reintroduced to the process by recirculating sludge from the secondary clarifier, and air to drive the process. So activated sludge processes are actively mixed and or aerated. Aerated zones are typically called oxic or aerobic, and mixed zones with no active aeration are typically called anoxic and anaerobic. And those distinctions will become more important as we move into specifics. So there's no photo here for lagoons. We'll talk a little bit about them with a few slides later on. But basically ponds that provide largely passive treatment, depending on the depth of the lagoon, in terms of and the aerial extent of the lagoon. The surface is usually somewhat aerobic, and then as you go deeper into the depth of the lagoon, it becomes more anoxic. Because lagoons generally have few or very minimal mechanical inputs, their footprint is usually larger than that of a comparatively sized capacity activated sludge system. And then trickling filters are depicted in the bottom left figure. A trickling filter is probably the most common example of attached growth processes historically used at wastewater treatment plants. Attached growth basically means that the microorganisms, instead of being free floating in this mixed liquor, they basically have a solid substrate to grow on. Generally, most trickling filters aeration is passive. It's just what comes in as the liquid, the wastewater trickles through the filter, but there are instances where there's forced aeration by blowing air into the bottom of the filter. So this is an overall summary of the case studies and their some of their main attributes. The columns are pretty self-explanatory here. As you can see in the second column, we had a wide variety of capacities, ranging from about 50,000 gallons per day to almost 100 million gallons per day. All of the case studies ended up being some variant of activated sludge, oxidation ditches, sequencing batch reactors, extended aeration, and others. So no lagoons were really found in terms of real practice that met those criteria that I mentioned earlier, and no trickling filters. The implemented modifications, the next column there, varied. We'll talk more about those specifically in a moment. Most of the case studies focused on optimizing nitrogen removal, as Dr. Kolinsky mentioned. Phosphorus removal is certainly of interest, although maybe not as lower hanging fruit as the nitrogen removal opportunities for optimization. And we'll talk a little bit more about what those specific modifications entailed in a moment. Looking at the total nitrogen data, it varied widely between plants. As I mentioned, some of the plants of that sort of subset of case studies that didn't meet all the criteria had already pretty good treatment for nitrogen. I think the low is about 5 milligrams per liter, which is a pretty advanced treatment. But we also had that range up into the upper teens of milligrams per liter of total nitrogen, which essentially represents plants with no enhanced nitrogen removal. Most of the systems had implementation costs. We call them capital costs here, but it's not necessarily for buying equipment necessarily. It's really more implementation or upfront costs, ranging from virtually nothing to a couple $100,000. A few were more than that, especially for larger size systems. And most of the systems realized operational savings rather than increased costs over time. So in an effort to summarize the case studies, we divided potential optimization approaches up into 5 main categories. The first 3, aeration modifications, process modifications, configuration modifications, those 3 in particular have a lot of overlap. In other words, if you're making modifications, which almost all the plants really had some efforts there, it's likely that you'll also be making some supporting modifications to process controls or process configuration in order to really get the best optimization of nutrient removal. So this slide shows an even finer breakdown of potential optimization modifications and which modifications each of the case study plants used. And these again are highlighted in detail in those case studies, which I'll hit at the end of my slides. But this and the previous two slides are mainly to give you a flavor of how we analyzed things, how the case studies were synthesized, and how they were summarized in the report. These couple tables were more or less directly out of the report, aside from a little bit of formatting. But again, we'll circle back to some of the specific optimization efforts shortly, and you'll hear even more detail about specific modifications from subsequent speakers. So before we jump into the specifics, just a little bit more primer on wastewater treatment, specifically as it relates to nutrient removal. Although this slide and the next slide, which is on phosphorus, they're greatly simplified. They should help better understand some of the more important factors that go into enhancing nitrogen and phosphorus removal, and likewise to understand the optimization approaches that are most likely to be successful that we'll talk about in subsequent slides. So removal of nitrogen during wastewater treatment is overwhelmingly a biochemical process, biologically mediated process. There are several pathways for nitrogen transformation during treatment that are shown there, but the one that we typically exploit when seeking to optimize an existing process is traditionally simply called biological nutrient removal. And what biological nutrient removal refers to is a sequential process of nitrification followed by denitrification. Nitrification requires, among other things, oxic or aerobic conditions, in other words, aeration. Bacteria convert ammonia into oxidized form, primarily nitrate or NO3, and then under subsequent anoxic or unaerated conditions, the nitrate is biochemically reduced to dinitrogen gas, which is harmlessly released to the atmosphere. Remember, our atmosphere contains about 78% nitrogen, so it's completely harmless. In addition to alternating oxic and anoxic conditions for nitrification and denitrification, another key prerequisite for effective biological nitrogen removal is having a sufficient amount of degradable carbon in the denitrification or anoxic reactor. Phosphorus in wastewater behaves much differently than nitrogen, so the approaches are a lot different. There's no option to convert phosphorus to a harmless gas that can be released to the atmosphere. Instead, phosphorus is typically removed by sequestering phosphorus in the wastewater solids and then separating the solids and disposing them, but separating them from the treated effluent. Although there's a way to biologically enhance the amount of phosphorus that's taken up by cells, it often requires the construction of new infrastructure. So generally, we weren't really looking at those efforts as they kind of crossed the line into a pretty intensive process. And frankly, most of the case studies where they were focused on low-cost phosphorus removal and the plant was not designed for phosphorus removal, most commonly we saw chemical precipitation used. Chemical precipitation is very well documented in guidance manuals and so forth, so we didn't really focus on it in the case studies. So now we're going to talk specifically about the three main types of wastewater treatment systems considered. That's, again, activated sludge, lagoons, and trickling filters. This table just provides representative concentrations of TN and TP in raw wastewater and in different treatment processes. As you can see, in general, without advanced, specific nutrient removal processes, the three main types of systems yield pretty similar results, although lagoons can often have lower concentrations of total nitrogen and phosphorus, mainly owing to the fact that they have relatively long retention times compared to activated sludge and trickling filters, but basically in the same neighborhood in terms of treatment efficacy. So we'll start out by looking more closely at lagoons. This figure shows a typical facultative lagoon. Facultative essentially means that the surface is aerobic, which is due mainly to wind-aided aeration and diffusion of oxygen into those upper superficial layers, with more reduced or anoxic conditions as you go deeper into the lagoon. You can read the predominant removal mechanisms there for nitrogen and phosphorus in lagoons. So for lagoons, we were able to find some documentation of enhanced nutrient removal approaches in the literature, but we were unable, as I mentioned before, to find examples where these techniques were being utilized in the real world and documented as we needed for a case study, essentially. The primary option that we came across was simply referred to as controlled discharge. It's basically what it sounds like. It's basically just controlling the discharge from the lagoon to coincide with times when either the effluent concentrations of nutrients are lowest or when the receiving environment impacts are anticipated to be lowest. And just to clarify there, the effluent concentrations are generally going to be lowest in the summer, particularly late summer when the reaction rates are highest and there's been time for volatilization and so forth. Although, especially if you're dealing with a discharging system, you know that receiving water impacts are often exacerbated during warmer weather. So those don't line up really well. However, a good number of lagoons use non-discharge systems for effluent management, spray fields, for example. So controlled discharge would work particularly well for these systems since the time of year when effluent concentrations are expected to be lowest coincide with when the water demand for irrigation needs are going to be highest, again, during the warmer summer months. As you might surmise here, controlling discharge from the lagoon requires a couple things, major things, which is a way to store significant amounts of water and a way to control that discharge, so adjustability there in the discharge level and volumes and so forth. So just things that would need to be considered before adopting this kind of approach for an existing lagoon system. So only one slide here for trickling filters. Most of what we found in the literature described pretty intensive types of retrofits to basically convert trickling filters to some type of biological nutrient removal system. So required a fair amount of infrastructure and capital costs. There are some process control types of efforts that are listed, bulletized there kind of at the top that may be applicable, but the documentation and again, particularly any documentation of real-world practice was very limited. These are sure to be very case-specific, context-specific. So, of course, I saved the best for last. All of our case studies focused on activated sludge, and there are a lot of options available, a lot of things that could be considered for optimizing nutrient removal in activated sludge plants using low-cost approaches. So as we talked about a few slides ago, nitrogen removal in particular is highly dependent on controlling the redox conditions within the process, so that's whether it's oxic or aerobic versus anoxic or anaerobic. So it's no surprise that the first series of modifications listed here are controlling aeration and improving aeration, so you have better control over those environments. Aeration interventions are listed but can include providing simple on and off controls for aeration systems that don't have them, more responsive controls potentially tied to real-time monitoring of those important redox conditions, as well as the addition of mixers to improve the efficacy of anoxic treatment that's required for denitrification. So as you can see here, and Dr. Galinsky mentioned this, which was great, there's a huge relationship between nutrient control and energy management, very synergistic. Aeration clearly represents the single greatest energy demand within most wastewater treatment plants, namely activated sludge plants. Over-aeration to some extent is common, it's wasteful, it's costly. So the reason so many of our case studies saw significant decreases in operational costs is because reducing aeration reduces energy use, reduces costs. I think we saw this come from both sides. We saw case studies where the focus was on nutrient reduction and, hey, wow, we're saving a lot of energy and costs. And then there's coming from the other direction too, or at least recognizing that these two things are closely intertwined and efforts to reduce energy are most likely going to result in improved nutrient reduction, particularly nitrogen. There's a variety of process-related interventions that can significantly improve nutrient removal. We don't have time to get into the details, but some possible process optimization activities are listed here. And of course, they're documented in the report and the case studies. And likewise, modifications to improve or modifications to process configuration can support aeration improvements by providing more favorable conditions for biological nitrogen and or phosphorus removal. Many of these modifications under the configuration and the process previous slide, as well as the two that I have listed here under the chemical heading, are really focused on providing degradable carbon as needed to support denitrification and anoxic processes, and it's also needed for enhanced biological phosphorus removal, which I mentioned generally requires more capital-intensive retrofits. So the report, of course, includes all of this information that you're seeing. It also includes some simple tools or discussion to allow plant managers, operators, and other stakeholders to think strategically about their plant and their operations and help them sort out which types of modifications would be most practical to pursue. So this table represents one of the tools provided in the report. As I mentioned at the start, the wastewater treatment plant case studies really constitute the new and novel information that this report provides. The background information that I went over, even some of the specifics on optimization potential, that's out there. But what's not really out there now until this report is really good documentation of the types of plants we targeted and the types of interventions, these low-cost interventions that we targeted, with really pretty solid monitoring data and cost data, as well as some other discussions that you can see bulletized there on the left. So in addition to the summary and synthesis of the case studies that I mentioned in earlier slides, there are actually pretty detailed 4 to 10 page summaries of each of the 12 case studies, which are provided as appendices to the report. And then my final thoughts before we move on to the case study, a couple case study presentations themselves, are bulletized here. I would dare say that some optimization is almost always possible. Making it happen is generally not a technology limitation. It really comes down to having a person or a team of people who are motivated and empowered to be able to make modifications that optimize their plant. Part of being empowered means having some freedom to experiment. That can be challenging. As you will see in some of the coming presentations, optimization is an ongoing and very adaptive process. It includes and requires a much deeper learning and a deeper understanding of how your plant operates, and particularly how your plant responds to different conditions and different interventions like changing process controls and so forth. As a general rule, some excess capacity is ideal. We didn't really look at that in particular. However, again, like with the first bullet, I'd say that most systems have some excess capacity. In other words, they're not operating at full capacity on a constant basis. So there's almost always some opportunities to optimize. Although we didn't focus much on phosphorus removal, since most efforts, as I mentioned, relied more on chemical precipitation when they really needed to reduce phosphorus significantly, we do generally see some modest improvements in phosphorus removal when nitrogen removal is optimized. I think that's mainly just a function of better overall control and more consistent operations of the facility. And perhaps most importantly, as I mentioned up front, it's pretty obvious from our work that this topic is currently underreported and underdocumented. It's a very important topic if you are a manager or otherwise a stakeholder dealing with what most of our plants are, which are resource limited. There's always resource limitations. So additional efforts to build nutrient reduction capacity and knowledge at these types of facilities is warranted. And certainly we believe that this report and the webinar represent really good initial steps to build capacity along those lines. So sorry for the technical difficulties. Hopefully you all have heard me for the last 20+ minutes, and if we have time, I can certainly take questions.
Okay, thank you very much, Vic. I think most folks heard him. I appreciate you providing the background of this recently released draft report, and now Tim is going to share some questions from the audience.
Yeah, thank you, Vic. We could hear you pretty well. Just a slight feedback. So in a couple cases, I may field the question and answer it, but otherwise, I think we're going to pass most to you. So we have a few questions in here that are rudimentary of sorts. Again, I wanted to emphasize that POTW stands for Publicly Owned Treatment Works, and that's basically your local sewage plant, sometimes large, sometimes small. As Vic said, we looked at a wide variety of sizes as best we could in the case study. So we had a question about the energy use, and I think we had a slide, Vic, that you provided that showed the basic energy use of a POTW, but could you provide some more detail about what kinds of energy savings folks might be able to see with this type of, the types of modifications we saw in the case studies?
Sure, I could try. Would have to go back, and you guys can tell me, can I go back in my slides?
Yes.
Yes.
Okay. Yeah, if we go back to the summary slide of case studies, which was way up front here, certainly for the case studies that we looked at, we did document operational costs and savings, and you can see there, you know, I think that some of the entries here are, you know, it'll say 0 costs or savings. Well, that might mean more that it wasn't really documented, but it wasn't really significant enough to even note. But in other cases, and John, I think, is probably going to talk about this in the next presentation, pretty well documented savings. You know, he has for Crewe roughly $17,000 a year savings. So you can see the magnitude there, and I think it's fair to say that what you're looking at in that last column there are mostly attributed to energy savings. And some fraction for some of the case studies, you're also seeing maybe some chemical savings, but I'd say the energy savings are a much higher proportion of those numbers that you're seeing there. So I'll let that slide answer the question.
Great, thank you. So when we started the case studies, how would you describe what we call the low-cost retrofit or modification?
Yeah, well, we had a lot of discussion about what that meant. We didn't define it as a cost number threshold because we were dealing with plants from 50,000 gallons per day to 100 million gallons per day. We basically looked at it, there's some subjectivity in there in the sense that we looked at it as basically not building new tanks, and to some extent not wholesale replacement of mechanical equipment. So most of what we ended up with, again, through this sort of iterative process of going through the case studies, the capital cost that you see, so really the investment up front, really in most cases relates mainly to control systems and monitoring. That feedback loop, those things are connected. So, and again, monitoring could be, you know, just simple dissolved oxygen or redox probes, but, you know, possibly wired into, you know, more elaborate or complex algorithm for determining on and off or, you know, variable aeration rates. So it includes both that sort of control side of it as well as having the ability to change redox conditions in reactors by, you know, throttling back aeration or on and off control of aeration, which requires the appropriate drives and so forth.
Okay, great. Thank you, Vic. I'm going to ask a question and answer it here. Did we consider privately owned treatment works in addition to publicly owned? No, we didn't. We looked at publicly owned treatment works primarily because we're looking at biological processes for nutrient reduction, and in a lot of privately owned treatment works, things can vary. The streams coming into them can be quite different and include a lot of industrial wastewater that may not be present in our publicly owned, but also the availability of data in a publicly owned treatment system was advantageous for us. But the principles applied here, if you have a biological system in a privately owned treatment works, could apply. We just didn't look at that as our design criteria for our case studies. And, so we'll have a couple more questions. One of them was a question about, apologize folks, I'm reading questions as I go along, and there are some being submitted, so bear with me as I get back to the ones I had highlighted. Just a moment. Did we, Vic, this is a question for you. In general, folks had questions about the achieved levels and whether or not there are targeted levels and how those relationships, what we can say about them, for case studies for the discharges. Do you have any comments about that?
Yeah, that's a good question. I don't, offhand, it's hard to generalize. There's certainly that documentation is in the case study summaries, really sort of under the heading of why did you do this? What were your drivers? And they varied a lot. So I hesitate to say specifically, but I would say in most cases, although I think maybe John will comment on this a little bit, in that I think he had some, pretty straight up regulatory drivers to improve, but most of the time the case study contacts did not say we were targeting, an effluent concentration of 10 or 5 or whatever. So it didn't have that really tight, numerical target that, we might think of if we were designing from scratch. It was sort of, what can we do? What's the best we can do here to, buy us more time before we do have to do something more intensive, or, again, there are these other drivers as to why these optimization efforts were pursued that are really context-specific, case-specific.
Okay, thank you, Vic. And along those lines, I'm going to interject is that, in general, these case studies are looking at empirical examples and specific plans, site-specific designs, so they have a lot of engineering and cost factors specific to them. And we just wanted to say that, in general, the levels that these folks achieve are what they achieve themselves, but this is an appropriate use of this information to, let's say, transfer that for a permitting requirement to someone else. These folks all have their own individual requirements that they're attempting to achieve, but these processes and our case studies give you an example of what the types of treatment levels can be achieved with these changes. So with that, we're going to proceed on to our next speaker. Thank you all for your questions. We may not have answered them all yet, and we may not answer all the questions, as we said, but we're trying to get through those that we can. Thank you.
Okay, thanks, Vic and Tim. I'd now like to introduce John Rico, who is the Superintendent of Water Utilities for the town of Crewe, Virginia. He's going to present our first case study.
I'd like to thank everybody involved with the webinar and involved with the report, especially Mr. D'Amato for all of his work in gathering up this information. I'd like to thank you for allowing us to participate in the report and in the program. We're always very excited whenever we get an opportunity to share our results and our success. And in this forum, I would tell you that in over 22 years as an operator, some of the best information regarding treatment that I've ever received or ever put to use came from other operators and other treatment plants. So I think this is a very important forum and a very important topic for us to be discussing, and I think the report is extremely important, especially for any facility that is seeking regulatory compliance with modest capital expenditure. Victor said something that really just hit home when he said he thinks that the motivated and empowered people are the ones and operators that can really make a difference. And those two terms really summarize for us here in Crewe how we were able to achieve what we were able to achieve. I've got some extremely motivated operators, and the town was extremely liberal in allowing us to do what we needed to do, mainly do experimenting on a daily basis, some increased testing, process testing, so that we can measure our results on a regular basis. So that really hits home when we talk about what it takes as far as on a case-by-case basis and on an operator level, motivated and empowered. That's excellent. I think when I was putting together the information for my presentation, I came across some numbers that really kind of floored me. Currently, the US EPA has over 43,000 impaired waters listed throughout this country. And of those 43,000, over 17,000 of those are directly related to nutrients and nutrient enrichment impacts. For me, I think the most important part of the manual is that it demonstrates that there are real avenues that can be investigated towards nutrient reduction and at an operations level. You know, our story covers several years, from our initial attempts to see if it was something that we could do to finally gaining consistent control of the numbers. On January 1st, 2007, the town of Crewe wastewater treatment plant began operating under the Virginia Pollution Discharge Elimination System permit, the watershed general permit, for nutrient discharges to the Chesapeake Bay watershed. The permit placed restrictions on the amount of total nitrogen and total phosphorus that were discharged from the plant. This was a new permit in addition to our normal permit, and it was going to require treatment techniques be established here at the plant that previously had never been employed before. The plant as it is, and it's a suspended growth process, an oxidation ditch plant, was built in 1996. And the nutrient limit strategy wasn't really established until 2005. So as designed and built, our facility didn't have nutrient reduction with regards to structures, equipment, controls, anything beyond the nitrification process. Our treatment, which is biological, was really just the removal of the organic content in the form of BOD and complete nitrification. In addressing compliance with the new limitations on total nitrogen, our treatment process had to be upgraded so that we could now create and maintain a treatment environment that was going to accomplish denitrification, which we've never done before. And denitrification is the reduction of nitrate, NO3, to ultimately nitrogen gas. It's really a three-step process. It's ammonia to nitrite to nitrate. In simple terms, this meant creating and then maintaining two very different environments with regards to dissolved oxygen in our plant. We had to maintain one with, and we had to create and maintain one without free available oxygen. The facility always had maintained excellent efficiency in the nitrification process. We just had to maintain the environment that was already rich in the dissolved oxygen throughout whatever steps we took in attempting to create that new second environment, a denitrification environment. That was going to require us to create and maintain a treatment stage that would now be void of free dissolved oxygen, but that was going to contain the microbial required combined form of oxygen, NO3 or nitrates. Without establishing both of these two very different stages of treatment, by some means, compliance with our new total nitrogen limits would be impossible. We had preliminary engineering reports that estimated a necessary cost from about $500,000 to just under $1 million. So this kind of facilitated our in-house work to see if we could in fact find some type of a treatment solution that would meet our treatment goals while at the same time keeping our capital costs minimized. The case study in the written report details all the steps that we took in order to get to the point where we are now. And this presentation will summarize the case study. You know, as you listen to me at this point, I've already used the term environment 6 times. And you may be wondering, what does environment have to do with wastewater treatment, and why does he keep talking about environment? All biological treatment processes have their success determined by creating and maintaining the proper environment or habitat for target biological organisms or an organism. You create a specific, stable environment that will then attract and allow to predominate in that environment or habitat a specific or target microbe. In this case, we're talking about bacteria. Those bacteria then accomplish a specific or target treatment. For nitrification and denitrification processes, we're dealing with 2 different groups of bacteria. They colonize their respective habitat or environment, and then they accomplish their respective desired treatment processes. If you'll forgive me, I like to borrow a line from a famous movie. If you build it, they will come. And that's absolutely true when it comes to wastewater treatment. If you build the habitat or environment that will allow a specific bacteria to predominate, they will. And in that environment, they accomplish specific treatments. The environmental control is mandatory in order to get any treatment goal success. And this is whether we're talking about treating the 50,000 gallons a day, 500,000 gallons a day, or 50 million gallons a day. The difference is the scale, the equipment, the facility, but the treatment principles will always be the same. Required environmental or habitat parameters for success when we're talking about reduction in total nitrogen. You have to have control of dissolved oxygen levels in different stages of treatment. You have to maintain an aerobic environment that has sufficient free available oxygen in one treatment stage for nitrification. Then you have to eliminate the free available oxygen in a separate treatment stage in the anoxic zone to accomplish denitrification. These are two distinctly different, almost diametrically opposed environments, but they're equally important because they're mandatory in order to achieve total nitrogen reduction success. You have to control and maintain pH and alkalinity requirements, and they're very specific. During the nitrification stage, pH and alkalinity control is critical. And those two parameters can either enhance the process or they can limit it. And in extreme cases, extreme swings in pH and alkalinity can actually stop the process. Controlling and maintaining sufficient carbon source or a food source. In the denitrification process, you have to have sufficient carbon source to complete that process. On the opposite end of the spectrum, in order to accomplish the nitrification stage, you actually have to limit carbon source concentration. But whether we're talking about nitrification or denitrification, paramount to removal, we have to have available in the select environment the item or the constituent that we're seeking to remove. In the aerobic stage with plenty of free dissolved oxygen, we have to have ammonia, and that's where we will convert it. The end result is nitrates, and then in the following stage, the anoxic stage, that's where we will remove the nitrates where the ammonia has already been depleted. So for us here in the town of Crewe, the big question, can we achieve the controls with the existing facility we have, our structures, and our equipment? And if we could, how could we go about doing it? The biggest challenge for us was going to be creating and maintaining those two absolutely necessary dissolved oxygen environments and being able to do that with the existing equipment. At the time that we took this project on and we were coming into compliance with total nitrogen limits, we were exclusively a one environment treatment plant or one habitat, and that was abundant free dissolved oxygen throughout. So our starting point was Chief Operator Jason Lewis and I visited a number of facilities here in Virginia that were practicing biological nutrient reduction so that we could see the specific treatment techniques that they were employing. And we adopted the philosophy that we know we can't afford the same equipment, but we can mimic the treatment technology. Not so much how they were doing it, but what they were doing. And because the treatment is all about environment, looking at the facilities here in Virginia was paramount. Climate is extremely key. I mean, you can go online and find solutions, but they have to be solutions that fit your specific needs. Our issue to begin with was, this is a look at our oxidation ditch. Our treatment process consists of 3 concentric channels. The waste stream being treated works its way through each one of the 3 channels. At the onset of our project, all 3 of these channels provided basically the same environment, the same habitat. They were all high in free dissolved oxygen. All three channels are controlled by the same aeration equipment. There's one long shaft controlled by one motor and no independent control for the specific channels. All the control was manual. We had 3 different speed settings. You were either running on high, low, or off. And we do have 2 motors and 2 shafts. They're identical, and they're on opposite sides of the circular channels. So our challenge with the existing structure and equipment was to create that opposite environment, the environment that's very low to ideally 0 in free dissolved oxygen. And we needed to do that in at least one channel while we still maintained that high oxygen level in at least one channel. So the first attempts were, as you look at that picture, you'll see there are discs on the shaft. And we tried to remove some of the discs, which was the prescribed way to alter the dissolved oxygen content in a respective channel. That lowers the surface agitation, and so that lowers the dissolved oxygen levels. The discs provide not only oxygenation, but they also provide mixing. So when we removed the disc, the DO was in fact lowered, but it began promoting settling, and it lowered the mixing. And when we're dealing with a suspended growth process, activated sludge, mixing is what brings the pollutants into contact with the microorganisms, which remove them. So that wasn't going to work for us because the mixing energy was lessened, so the mixing was lessened, so the removal efficiency was lessened. So after altering our disc configuration, we tried to see what kind of results we could get if we manually cycled our rotors or those discs off and on. And in doing that, this plant is not staffed 24 hours a day. We could only do the manual on and off cycling while we were here, so that didn't give us a real picture, but it did show that we could get some success. And in fact, by altering that on and off cycle, we could get some successful results. So we went to the next step, and that was we installed 24-hour programmable timers that had an on and off control, but they had no response to changes in flow and changes in temperature. And with wastewater treatment, 2 very key parameters are going to be flow and temperature. They're going to drastically affect your treatment results. So with this programmable timer, we didn't have any response to that. So we did see some success, better than the first step, but not enough that it was something that we could even contemplate putting in as a permanent fix. We had an online dissolved oxygen probe that has high and low controls, and with that linked into the rotors to cycle from low to high, we found a system that responded to changes both in plant flow and in temperature. It's a simple set point control system. As we tried in the first example with the 24-hour timer on and off, with the online dissolved oxygen probe, we were able to take a very inexpensive, less than $200 controller and enter set points. For example, the low point was 3.0, the high point 3.5 milligrams per liter of dissolved oxygen. The dissolved oxygen probe would see the dissolved oxygen content. When the level dropped to 3.0, our controller would kick the speed to high. That would increase the dissolved oxygen to the point where it hit 3.5 milligrams per liter, and then the controller would kick it back to low. So we were cycling between 3.0 and 3.5. We've since tightened down to where we usually are only about a 0.2 difference. Currently, we're from 3.5 to 3.7. But it gave us a really good control, and it gave us really good results. Really good, but just not good enough. We were still finding that in the free available oxygen, we were finding in our anoxic zone. And when you have free available oxygen available, the microbes that are involved in the denitrification process utilize that free oxygen during their normal metabolism, even if you have a combined form like NO3 or nitrates also available. So for us to attain a true anoxic zone, a zone that only had the combined form of oxygen or the nitrates available for the target microbes, we had to get the dissolved oxygen level in our anoxic zone down and discover exactly where that extra free available oxygen was coming from and how we could eliminate it. So our task was find the source and eliminate it. Now this is not a picture of our facility, but this is one that represents exactly the issue that we were dealing with. We had our return activated sludge, the discharge piping, that discharge above the water surface or the mixed liquor surface in our anoxic zone channel. We also had the introduction of our influent, the water entering the plant, discharging in the same zone several feet above the surface of the channel. And working on the exact same principle as those discs do, surface agitation imparts dissolved oxygen. So having these pipings discharging that high above the surface, as you can see in the picture, created a lot of surface agitation and as a result imparted a lot of dissolved oxygen. And then in addition, the plant was designed originally so that at the influent, the water coming into the plant, it goes through a grit removal process where the heavier solids settle out. And in part, to accomplish this, it went through an aeration channel. That was also imparting dissolved oxygen into the waste stream. So we discontinued the aeration and we added, and this is our plant, you can see we welded on extensions onto that discharge piping so that we had our discharge point below the surface of the water or the mixed liquor in our anoxic zone channel. This elimination of the surface agitation and the additional oxygen from the aeration at the beginning of treatment to the ditch provided us with the target environment with regards to dissolved oxygen and gave us exactly the results that we were looking for. Once we had those two opposing dissolved oxygen environments established and in place, we found that through some testing, we lacked a supplemental carbon source. For simplification, carbon source is equivalent to food. And even further simplified, the philosophy is if we keep them eating, then they will continue normal metabolism, which in the anoxic zone, the zone we are trying to remove the nitrates from, the NO3, if they're eating, they're going to continue to convert nitrates to ultimately nitrogen gas. We went through a step-by-step process of following the food as it entered the plant. And we found that the channel prior to the anoxic zone, the food coming into the plant wasn't sufficient to carry over. So we added a supplemental carbon source, additional food, over the course of 2 years, finding that a molasses product gave us the most bang for the buck. We originally were using a dry molasses product, very simple for the operators to use, very safe, easy to get, easy to store, and that really showed results. We used a number of other products in our attempt, but for the cost and the result, the molasses product did the job. Then in 2011, we were contacted by a company that has a specific molasses-based product that they use primarily for enhanced biological phosphorus removal. They contacted us and asked if we would like to have a free trial, and of course, not being someone to pass up the opportunity to have free trials, we jumped all over it. So they actually even brought us in a tank, they brought us in a pump, they brought us in the product, and the product provided excellent results for both total nitrogen and total phosphorus removal. And the total phosphorus removal was really unexpected, and the best unexpected part was by getting the biological phosphorus removal, which previously the only means of phosphorus removal we used was chemical phosphorus removal. We used liquid alum. Being able to lower our liquid alum usage by 50% enabled us to realize a significant cost savings when it came to the phosphorus removal. So the final piece of the puzzle was management of our side stream contributions to total nitrogen in the form of nitrates. Now, for those of you who are not aware of it, a side stream is a waste stream that enters the treatment that originates somewhere within the treatment facility itself. We were correlating spikes in our effluent total nitrogen, and this effluent total nitrogen came in the form of elevated nitrates. We correlated that to normal operations of our aerobic digesters. Aerobic digestion is the biological process where the solids are held and aerated without putting any additional food source to them. And in the presence of the oxygen, the microbes will stabilize the sludge and reduce the volume of the sludge that you ultimately have to dispose of. During the digestion process, because the mass of the microorganisms is being reduced, when you let that settle, you have clear water at the top. So we were seeing these spikes when we were decanting, which is allowing the sludge to settle, and then drawing that clean water off the top. And also when we were going through the dewatering process, and dewatering is when we take sludge from those aerobic digesters, we run it through what's called a belt filter press, which basically squeezes the water from the sludge, giving you a dry cake, which you can ultimately dispose of. So whenever we were doing our dewatering or decanting, we were seeing these spikes. So when we started running the numbers on our aerobic digester, we found that we were having through-the-ceiling results in nitrates. Simply because they were aerobic digesters, the aeration on those units was nonstop. And the abundance of dissolved oxygen, that aerobic environment, created extremely high concentrations of NO3 or nitrates. So we just thought about it and used the same treatment strategy we did to reduce the nitrates in our ditch by limiting the dissolved oxygen. So we installed very simple 24-hour programmable timers, 2 hours on, 2 hours off on our digester aeration systems, and that limited and allowed us to control that free available oxygen in the digesters. When we came up with the exact right amount of on-off cycles, it completely eliminated those spikes. And this is a look. One of the questions to Victor earlier was what the numbers are in relation to target limits. Well, this is a look at our summarization from 2005 through 2014 of total nitrogen. You can see on the second column going across our total annual average for total nitrogen in 2005 and 2006, which was prior to putting any controls in, was 7.11 milligrams per liter and 8.59. Below it, the new total nitrogen annual limit in milligrams per liter for us is 6 milligrams per liter. So in those 2 years, we exceeded no matter how many pounds we discharged. But in 2007, once we got our strategy in place and we got our controls in place, you'll see a significant difference. You can see that beginning with 2007, where we were above on our annual average and percent change, we started dropping below. And 34.2%, and on average, averaging about 40% reduction between what our limit is of 6 milligrams per liter and what we discharge on an annual basis. Here in Virginia, we have a total nitrogen discharge pound allotment. And that comes because we are regulated on the Chesapeake Bay watershed. So the receiving streams that this facility discharges into ultimately discharges into the Chesapeake Bay. And the Virginia system works, and it may work this way around the country, but in Virginia it works through the nutrient credit trading program. We have, for example, we belong to the James River watershed. And there are a number of facilities that are part of the James River watershed. There's a total pound allotment per year for the James River watershed, regardless of the number of facilities. The facilities work together for the ultimate goal of meeting that limit for the watershed. So if you have some of the facilities who actually are discharging a higher poundage, the facilities like ours that are discharging a lower poundage are able to sell credits through the Virginia Nutrient Credit Exchange Association. That benefits the facilities that need them. It benefits the facilities like ours, which allows us to realize a financial gain because we're meeting our limit. we're discharging less pounds, and those pounds have a dollar figure that is associated with it. So when we are able to save 6,000, 7,000 pounds per year, doing the math on it, we end up having a financial realization that really benefits the town of Crewe. And down at the bottom of the chart, you'll see that on average, we're well over 70% for the total nitrogen poundage below our allotment. So that allows us greater realization of that financial profit. This is a look at the same type of chart, but looking at total phosphorus. At total phosphorus for our facility, we have a total phosphorus annual limit of 0.5 milligrams per liter. This plant never had an issue with total phosphorus, but prior to putting in our current controls, all of the phosphorus removal was 100% chemical precipitation using liquid alum. Once we started using the liquid molasses product that is also fortified for enhanced biological phosphorus removal, we were able to realize phosphorus removal that allowed us to drop our alum usage significantly. And as you can see across the very bottom, we're looking at total phosphorus pounds on average about 95% below our allotment. As total nitrogen pounds realize financial gain, so does total phosphorus. Through the same nutrient credit exchange association, the total phosphorus excess pounds or credits can be sold, and the facilities that aren't meeting their goals purchase them, and it's all arranged through the association. But the bottom line is they're able to realize compliance. We already have compliance, and we're able to realize a financial gain. This is a look at the balance that we had to put in place when we talk about those two environments. We initially had just the one environment, which was an aerobic stage throughout the plant. The first column across the top, the total nitrogen annual average in milligrams per liter, prior to putting our controls in 2005 and 2006, the TKN, which is removed in an aerobic process, was below detection limit. Significantly, it was very rare for us to ever get a usable result. It was almost always below the quantitative level, less than 0.5 milligrams per liter. But on the reverse hand, the column underneath it, nitrates and nitrites, you can see that was significantly higher. And at the bottom, you'll see that in 2005 and 2006, all of our total nitrogen was being discharged in the form of nitrates. Beginning with 2007, when we put our controls in, we had to find that balance where we still maintained enough in the aerobic stage, while at the same time we were able to drive that oxygen down in the anoxic stage. The TKN numbers represent that aerobic stage. The nitrate and nitrite numbers, that represents the anoxic stage, the stage where we're limiting that dissolved oxygen, and you can see how we balanced out. We still have excellent TKN results. We're on average well below 1 milligram per liter. And at the same time, we've dropped down where we were nearing 10 milligrams per liter on nitrates down to 2.5 to upper 2s. So we were able to realize significant savings and significant balance just by putting these things into place. But to best demonstrate the savings and what was the, I guess, probably the biggest benefit to using the molasses product that we finally settled on was I had always been taught and always believed, because that's what the literature told me, that without a true anaerobic zone, and that's a zone there is no free available oxygen or any combined form of oxygen, without that true anaerobic zone, enhanced biological phosphorus removal is impossible. But these numbers right here kind of tell a little bit different story. At the bottom, the previous dry molasses feed rate, that represents the numbers and our costs from 2007 to 2011. We're using dry molasses as our supplemental carbon source, the extra food we needed to accomplish the process, and we're using liquid alum to remove the phosphorus. You can see that our total dry molasses and alum costs on an annual basis was in the neighborhood of $53,000. You look at the top, when we switched to the enhanced BioP, which is the molasses-based product, because it contains a higher sugar content, we were able to lower the feed rate, and because we were getting biological phosphorus removal, we were able to significantly lower our liquid alum usage to where our present total alum cost and our total enhanced BioP cost combined is in the neighborhood of $30,000, which is about a $23,000 a year savings. And the icing on the cake is the numbers have increased the sale of our nitrogen and our total phosphorus credits. So that just puts extra on top to where now we're probably looking at total savings somewhere in the area of $30,000 a year. So in 2012, our membership with the Virginia Nutrient Credit Exchange Association really began to pay dividends. As a result of the facility's success in total nitrogen and total phosphorus reduction, the surplus credit treatments have become a source of consistent revenue for our town. And with the additional savings in our liquid alum costs, the biological nutrient reduction program that we have in place not only ensures compliance with our nutrient discharge limits, but allows for positive cost impact as well. And I guess the bottom line is the job is never done. Even though our numbers are always good, we're always tweaking. We're always trying to find that one setting or something that we can do to drive those numbers a little bit lower. But ultimately, I think it goes back to, as I said at the beginning, the realization that at our level, on an operation level, we could actually affect a change that had a lot of positive impact financially for the town and expending just a minimal amount of money.
Okay. Thank you, Mr. Rico. In the interest of time, we are not going to take questions now from our audience. We're going to move on to our next final speaker, Mr. Gilbert Perez, the Director of Operations for the Victor Valley Wastewater Reclamation Authority. He's going to present the second case study, and then we'll try to have some additional, if there's time left, we'll have some questions. You can also contact the speakers that we have today directly. So take it away, Gilbert.
Good afternoon.
Good afternoon. Go ahead.
Okay. My presentation is on converting conventional activated sludge facility to a biological nutrient removal, utilizing in-house resources, obviously staff, and creative financing. Victor Valley Wastewater Reclamation is located in Southern California, what we call the High Desert. It is a regional wastewater reclamation authority in San Bernardino County. We currently treat approximately 12.5 million gallons a day. We discharge to the Mojave River, which is a NPDES permit, Title 22 water. We also discharge to percolation ponds, which is, we have a WDR permit. We also have a WDR permit for recycled water, which is also Title 22. Our solids are treated through anaerobic digestion, and we discharge our digested sludge to solar drying beds. Since we are in the high desert, we have plenty of sunshine, and it is a pretty dry climate. So we don't have no ammonia side streams coming back to the plant. We service the, since we are a regional wastewater treatment plant, we are a JPA, Joint Power Authority. We service the city of Victorville, city of Hesperia, town of Apple Valley, and some service areas from the county of San Bernardino. In February of 2008, the Regional Quality Control Board finalized our NPDES permit with a total nitrogen limit of 10.3 milligrams per liter and an ammonia nitrogen of 0.54 milligrams per liter. Now, in some of the other presentations I have seen where other facilities have much more stringent, but for us it was quite a challenge since this facility was designed as a conventional activated sludge plant. Our facility was designed for actually 18 MGD of conventional activated sludge. And these limitations were based on anti-degradation analysis of the Mojave groundwater basin, which indicated a trend of increased nitrates in groundwater. So due to this change and the new limitations, obviously we were faced with making significant modifications to convert the biological nutrient removal, BNR, for nitrification and denitrification. And due to the stringent nitrogen limits, the VWA facility capacity was reduced to 13.8 MGD. This equates to a loss of $42 million in equity overnight. One of the challenges that we faced was that during this time, the high desert was growing rapidly and being affected by a housing boom. The flow increase projections was calling for additional capacity at the regional treatment plant. In addition, the denitrogen limits impacted the capacity negatively. Losing capacity, again, if you all understand this, losing capacity at a treatment plant could also lead to a building moratorium, and this could have affected our economic growth of our service area. So that was a big deal for us and the service area. So based on these new limitations, we contacted engineers, and we did receive an engineering estimate of $13.4 million to install a fixed integrated film-activated sledge system. What it is basically you suspend media in the aeration bases. It gives you more surface area, and you're able to grow more biomass in your basins, which will help you with your nitrification and denitrification. And this would actually bring us up to 14 MGD. Remember, we went from 18 to 13.8. With the recommended IFAS, we would have only crept back up to 14 MGD. And the recommendation was made due to, by installing the IFAS system, we would not have to build additional new structures for biological treatment, and also due to funding constraints. In addition to that, there was also discussion with the regional board that were concerned about our solids dewatering facilities since we are using drying beds. They were concerned that nitrates or ammonia was bleeding into the groundwater table. And actually they were calling to potentially force us to build mechanical dewatering facilities. And this would have added additional challenges due to the high ammonia side stream that we would have to take back to the plant, so that would have impacted our capacity even further. So what we did, we had an option, $13.4 million, or what we did is we gathered staff, sat around the table, and we discussed, what can we do with what we have? What can we utilize existing infrastructure and avoid capital costs? And what we did is we came up with a plan to improve our process and improve our efficiency in order to nitrify and denitrify. One of the things that we did is we focused on improving instrumentation for monitoring dissolved oxygen, airflow, ammonia, and nitrate concentrations. We also focused on the air diffusion system and basically evaluated our aeration system to identify any inefficiencies and repair them, such as replacing inefficient diffusers and repair any air leaks. Structural enhancements to provide system reliability was another one. We installed internal recycle pumps. Once all three project elements were completed, staff were able to meet their objective in meeting permit requirements and improving groundwater quality. Our total nitrogen went from 14 milligrams per liter to 8 milligrams per liter. So one of the things that I always tell staff here is that unreliable plant process or equipment affect plant performance and also increases operations and maintenance costs. So when you have something like this, the solution is quite simple. Make these components reliable. What we did by doing these simple things and involving staff, we avoided a cost of $13.4 million to construct the IFAS system. In addition to that, we did not have to eliminate the drying beds, and the regional board continued to allow us to use the drying bed and the percolation ponds. If we would have had to construct additional facilities for dewatering, that would have been an additional $10 million expense. Staff's improvements cost approximately $2 million, so our savings on this project was $21.4 million. Phase 2 of the project involved additional challenges, obviously to improve treatment efficiency and reliability. We focused a lot on energy savings, eliminated chemicals for alkalinity augmentation, and then we also had financial challenges. How do we do this? So what we did is we met with Southern California Edison, their electrical provider here in Southern California. And Edison educated staff here on creative financing options such as unbilled financing and financial incentives for energy efficient projects. What Edison did, they provided engineering calculations, equipment, material, selection, and funding. Now by Edison actually providing the engineering calculations and actually evaluating equipment, it made it a lot easier for us as a public agency to sole source this equipment and purchase it direct and install it. Now, on-bill financing is a program that Southern California offers. It finances qualifying energy efficient projects. So they evaluate the project for energy efficiency. If the project qualifies, it is approved, and basically the repayment of the loan is done in monthly installments, which could be added as a line item on your bill. And those are paid back through your savings. These funds are also available at 0% interest and no fees. It also reduces your monthly electrical usage. And on top of that, they offer financial incentives. Once the project is completed, they evaluate the efficiency of your project, and incentives are given. The phase two of the project involved installation or replacement of our diffusers with fine bubble diffusion through our aeration basins. And this graph here indicates or shows the savings that were acquired per project. Aeration basins 1 through 8, $228,000 a year on energy savings. Aeration basins 9 through 12, $63,000 a year. They also assisted us in evaluating turbo blowers, and we went ahead and installed 2 turbo blowers for a savings of $98,000 a year. And on top of that, incentives, we received incentives for 1 through 8 at $35,000 a year. One payment for $35,000. 9 through 12, we received an incentive of $14,000. And for the turbo blower, we received $47,000. On top of that, by making all these efficiency improvements, we were able to eliminate magnesium hydroxide by improving our denitrification and recovering alkalinity through denitrification. And that is a savings of $151,000 per year. So the total savings from phase 2 of the project is $638,000. Now, our journey has been a long one. We started back since 2008 when our nitrogen limitations were given. We understand that nitrification, denitrification is energy intensive. So we really focused on optimizing energy efficiency, adding automation, looking at new equipment, new technologies to assist us to meet this goal. So again, this is just a quick timeline of what we have done in our journey to also be efficient and meet our permit requirements. The operational benefits gained from this: simpler plant, reducing operating problems and related costs. We eliminated chemical handling. We improved air transfer efficiency, improving our nitrification. We reduced mixed liquor recycle rates and improved denitrification. And that was done by installing an automated logarithmic system to control our SRT. We were able to reduce our SRT from approximately 15 days to 4.5 days and still meet our nitrogen limitations. In addition to that, it also helped us to reduce our return activated sludge rate from an approximately 80% to approximately 30%. By doing so, we were able to secure 5 return pumps and not only operate with 1 pump. So that's huge energy savings there. And also it increases the life of your equipment. In addition to that, we were also able to secure, we have 10 secondaries. We were able to secure 6 of the 10, and currently we operate with 4. That also helped by decreasing the return rate. It helped us to increase our detention time in our aeration basins, which obviously that's going to improve your nitrification and your denitrification by giving you more detention time in your tankage. It also makes the plant much simpler to operate. Economic benefits provides an aeration system which is more efficient than the system we had. Lower overall electricity at the plant, about close to $300,000 a year. Alkalinity recovery, eliminating magnesium hydroxide usage at $151,000 a year. We reduced O&M man hours, and what we did is we shifted those resources to other areas of the plants to improve efficiency. Financial incentives, a total of $96,900. And again, eliminating the installation of fixed media, negotiating our waste discharge requirement permit to discharge to percolation ponds and the solid handling facilities. That was a savings of combined, it's a savings of $21,400,000. The other benefits that we gained, we increased plant hydraulic capacity, and then there's value from avoiding fines and noncompliance, and potentially increase organic and nutrient treatment capacity. Our next step is to have our plant reevaluated by a third party to see how much capacity did we gain above 14 MGD. So again, for every MGD, again, what I said at the beginning, we lost $42 million in equity. So whatever MGD we gain, it's a gain for our plant. Again, that concludes my presentation.
Thank you, Mr. Perez, for providing the case study on Victor Valley. And we're going to have time for some questions, but first I have a few announcements. First, I want to make sure that if you did not get your question answered today, shortly on the screen you will see that you can contact our speakers at their emails that are provided. So please use this contact information that's on this slide. And also, I want to let you know that we are going to have some more Watershed Academy webcasts this coming year. We're currently planning our next webcast, and we will announce it on our website in the coming weeks. So please do check back at www.epa.gov/Watershed Academy, and you'll see the details there. I also want to encourage you to download the certificate if you like. The certificate can be downloaded from EPA's server through the link that is provided on the slide. Please type in this link into your browser to download the PDF document. And you can also personalize the certificate with the names of everyone that is watching from your location. And finally, when the webcast is over, an evaluation survey will be shown on your computer screen. And we encourage you to answer the evaluation and give us feedback, as we always try to listen to the feedback and improve our webcasts. And now we'll have time for questions for our speakers, and Tim Connor will pose the questions from the audience.
Okay. Thank you all for sticking with us. We noticed that the number stayed high throughout, so we appreciate your patience through our technical difficulties, and thank you very much to our speakers. I'm going to start out. I think the overwhelming question that we received so far is for our Crewe, Virginia folks. Folks would like to know what the name of the product for the molasses was and where you got it, and a few more details. If you're able to pop back up.
Okay, can you hear me?
Yep.
Yes.
The product that we used is called Enhanced BioP, and we got that from a company out of Wisconsin, Quality Liquid Feeds Incorporated. If you would like to contact me by email, I can give you the contact information direct. But they're real good folks, and it's an excellent product and did a fantastic job for us here.
Okay. A follow-up question for you is, after your great success, John, do you anticipate, is there any mechanism by which you think you all might, in some folks' words, be punished for doing so well, having your allotments changed, or are you guys concerned about any down the road effects because you have done so well compared to what you were doing?
Not really. I've been doing this now for about 22 years, and at least here in Virginia, and I can't speak for the people at the US EPA, but I'm sure they're all great folks. But here in Virginia, the Department of Environmental Quality, here they're all about the results and all about achieving success. And I have not, in my experience, ever known them to do anything like that. I think that they have referred a number of facilities to us here to see just exactly what we're doing and how we're doing it, and asking our help and assisting them to try to get some of the same results.
Okay. I'm going to ask Ann to do a favor for us, or someone else. Could we back up to, folks are asking us to back up to 2 slides. One is the certificate slide to show it a little longer, and then also for the contact information. And I would also like folks to know, again, that this PDF will be available at the Watershed Academy website on epa.gov. It is available already. Again, we've had a lot of questions about how to download that. But John, thank you for your answer there. A related question for you all at the Crewe plant. There were some questions about, sort of your configuration and how things were oriented. Whether you all, where you added the molasses. Could you provide like a real nutshell summary of the process, step by step, as it looks today or after the modifications, and just a couple sentences?
Yeah, well, we add the molasses product at the head of the plant. We have a pump station that pumps the influent, so we add the molasses to boost the BOD content right at the influent to the plant, and that allows it to carry through the process until ultimately the denitrification stage where it's exhausted.
Okay, super. Folks, thanks for all your questions. I'm just looking through to see if we have any that we haven't answered so far. I think a lot of the speakers did a great job of answering questions that folks were submitting during and early in the presentation, so you all anticipated them very well. I think by and large, at this point, I think the majority of questions that we've received, there are some technical ones, and I think they're more in detail than we have the opportunity to go into here today, but I think we've answered the majority of general questions we've received. So I think at this point, I'm happy to turn it over to Ann to summarize things and take us out. But thank you very much to Gilbert and Victor and John for great presentation and great patience.
Okay, well, thank you very much. At this time, I'd like to conclude today's webcast and thank you all, to all of our amazing speakers, and a special thank you to Dr. Golinsky for taking time to provide an introduction of this webcast. And I do want to reiterate that we did provide the contact information. It is on that information is on the PDF of the slides that's posted on the Watershed Academy website. So you're welcome to contact the speakers if you have a really nitty-gritty question that maybe you weren't able to get answered today. So we thank you all for bearing with us with a little of our technical difficulties today. Thank you for joining us, and that ends our webcast today. Hope you join us again for the next one.